All right. Good morning, everyone. Welcome back to C69. Today what I'm going to do, I'm going to finish the part on paging, and I'm going to re-explain a few things. So again, you need to know how the virtual memory work, of course, for project 2, because you have to translate some addresses. Especially when you have a system call, the address that has been passed to the stack is most likely, a user, an address from the user space. So an address that is valid in the user virtual memory, okay, for that process, for that thread. And you have to translate it into a kernel virtual address, right? And so you need to know that for project 2. For project 3, well, you need to know a little bit more about how it works, especially the idea of how the virtual memory map into the physical memory. And also you need to know a little bit, you need to know a little bit more swapping. And that's what I'm going to do today in the second part of the course. So for now, let me kind of a quick recap about what's happening. So first of all, when a program executes, how low you can go, even at the assembly level and so on, the program manipulates virtual addresses, okay, always. You never see actually physical address. Behind the scene, what's happening is the CPU, when it sees an instruction with an address, it's going to automatically translate that virtual address into a physical address. And how does the translation work? Well, it's thanks to this, okay, the translation. And it's thanks basically to something we call the page directory or the page table. Okay, sometimes we call it the page table, but here I'm going to make a difference between the page directory and the page table. Okay, so that's mechanism here. It's a way to translate the address, the virtual address, to a physical address. So how does it work? Well, as I told you, the memory is divided into pages. Okay, maybe I should use the right term here, the same term that they use in Pintos. The physical memory is divided into frames. Okay, and each frame is a fixed size, 4 kilobytes. Okay, and so when you have an address, okay, so an address here, we are using 32-bit address. Okay, we need to translate a 32-bit address into the corresponding address here in the physical memory. And so the way it works is as follows, right? So what you have is, so this address here points to some kind of a virtual page, okay? So the page is virtual, and this page is translated to the corresponding frame, right? And so this is something that you're going to see again in the next tutorial. The idea here is you can have 2 threads that have in their page table, they have the same, they have different pages that point to the same frame, physical frame. That means that actually they're sharing memory in a way, right? So here, the idea is in the virtual address, every thread has its own kind of virtual space, right? And every thread, believe it, has the entire virtual space. That's how, for example, we can compile programs and, the program always starts at the same address and so on and so forth because it's virtual, okay? So how does translation work? On the x86, actually, we have kind of a 2 lookup translation, okay? So the first 10 bits here, here it's an index, right? The first 10 bits is going to give you an index in the page directory, okay? And the page directory is kind of some kind of the first entry of this translation process here. So then, once you have the index, you find the page directory entry, and the page directory entry points to another address, okay? And this other address is actually the location of what we call the page table, okay? And then on this page table, again, in this page table, there are 1,024 entries, okay? And then we look at the next 10 bits here of the address to find the exact page table entry. Once we have the page table entry, okay, the page table entry is going to be 4 bytes, okay? There's going to be, so there's going to be a few bits that are, we will see that are going to be useful, the modified bit, the access bit, and so on. But there is also the frame number. And now you can take the frame number, actually put it here instead of kind of these 2 indexes here, and this plus the offset, you get actually the physical address here. Okay, so that's how the translation works. A little bit of math that is kind of interesting, right? So maybe here, let me show you a little bit of math. I don't know if you see that. Let's see. Assuming that we have all the RAM that we can. Okay, so we are on 32-bit system. So that means that the entire address space is 4 million. Okay, so there are 4 million, 4 billion addresses. Right? But again, as I told you, they are divided into blocks of 4 kilobytes. So how many frames are there? Well, you can do 2 to the power 32. Oops. 2 to the power 32 divided by 4096 bytes. That's a million of pages. Okay, so there are 1 million pages here. So frame. So there are 1 million frames here. Okay, so it means that the address here that we can have potentially can be like frame 1 million. Okay, so we have 1 million frame. Let's see. So here, the first 10 bits here, it's going to give you an index. So how big is going to be the page directory? Well, 10 bits, it's going to give you 10,024, right? So it's 2 to the power 10, right? It's 10,024. So 10,024 entries. And I told you each entry is going to be 4 kilobytes. So, 4 bytes, 4 bytes. So 4 bytes multiplied by 1024, that's 4 kilobytes. How convenient? How convenient, because it means the page directory, again, this is information in memory, right? The page directory fit into 1 frame. Okay, so that means when you're going to divide, when the system boot, you have to understand that. When the system boot, what we do is the following. So I told you, right, there is the CR3 point register. So that's a register in the CPU, and it's going to point to the page directory, right? And we're going to have 1 page directory per thread. But when you boot, you boot the kernel, kind of the main thread, if you want, in PTOS. And so here, this CR3 will point to the page that contains the page directory. Okay. So then here, each index, so each entry here can point to a different page table. So how many page tables can there be, right? Maximum you can have, if you have 1024 entries, you can have a 1024 page table. And how many entries are inside the page table? Well, same thing, here the index is going to be 10 bits. So 10 bits means 10,024 page table entry. Each of them is 4 bytes. It means, again, 1 page table can fit into 1 frame. Okay, it's 4 kilobytes. And so here, how many page tables are there? Well, there are 1,024. How many page table entry in a way? 1,024 times 1,024. How convenient. This is exactly, it's written here 2 to the power 20. So, 10,024 multiplied by 10,024. And again, we find the million. And the million frame that it's in memory, right? You see all the math kind of add up here, okay? You're going to redo this map with the TAs and so on, okay? So again, this is something important. This is per thread, okay? So that's why each thread, potentially, they could map the entire memory, right? Most likely they don't, right? They don't need to map the entire memory. That's why this 2-step translation is creating some kind of a sparse data structure. Most likely, what every thread needs at least is, of course, 1 page directory, okay? And 1 table entry. So that means, 1 page directory and 1 page table. If they do that, it means at least they have allocated 1 frame, okay? If they allocate 1 frame, they will have that. Maximum with 1 page directory and 1 page table, if they fill all the page table, they can allocate 10,024 frame. Okay, that's already a lot. 10,024 frame. It's 10,024 multiplied by 4,096. It's 4 million bytes, right? So 4 megabytes. So you see here, a program can do that, and it can do that with allocating just this and this. So page directory and page table, meaning a process at minimum just need 2 frames, meaning 2 times 4 kilobytes, just to create a page directory and a page table. Okay. What is a frame again? Again, we divide the memory into frames. Okay, that's just wording. Okay, there is a concept of page or frame. Okay, this is all paging, right? But I'm using the same the definition that they use in Pintos. In Pintos, when they call frame, it's actually the fact that the physical memory is divided into 4 kilobytes block. Okay, I mean, some people call it frame, some people call it page, whatever. I'm here. I mean, I can call it also. I started to call it like virtual page or physical page, right? A physical page is basically a frame. Okay. So that's it. So here we need that per process. So that means that every thread at least needs 1 page directory, 1 page table. Okay, that's the minimum, and that means that they just need 8 kilobytes. And so if you have like I don't know 10 process, well, you just need 80 kilobytes. Okay, as opposed to our 4 megabytes that we had before, right? So that's how it's kind of sparse, right? And again, so now every thread we see is its own memory. So they will have their own page directory and their own page table. So that means that when we switch threads, okay, when we do the context switch, okay, when the scheduler kicking in and then we switch context, of course, we need to change the address translation. And here it's just changing this register actually. So in the same way that, when we do the context switch, we change the stack and we switch the ESP and the EIP, we also need to change the CR3. Okay, and we change the CR3 to point to the page directory for that thread. Okay. Question here. So each page directory entry corresponds to a single thread, and each page directory corresponds to a thread. Each page directory entry corresponds to a single thread. Yes, and each page directory corresponds to a thread. That's the same thing, I think. So yeah, so each thread we have its own page directory. Okay, and necessarily they need at least, if they have allocated, 1 frame in memory, at least they need 1 page directory and 1 page table, right? Of course, they can have many, right? So that's it. So yeah, they need that per thread, right? So at least I told you, right? At least every thread we need to allocate 8 kilobytes of memory just to manage the memory, right? So that means actually. When they need to allocate, assuming they allocate 1 frame, they need to allocate 3 frames. Okay, 1 for the page directory, 1 for the page table, and 1 for the what they want to store, right? So the information that they want to store. Okay, so that's the translation. They were asking, does each thread owns its single entry or the entire page directory? No, the entire page directory. No, this is per thread. Yeah, the entire page directory. Yeah. Each thread has its own page directory. When you're going to switch context, you're going to change the CR3 pointer to point to another page directory. Yeah. Okay. Mohammed Rahman asked here, how to create it? Why not skip the double translation and just have 1 big table that is 4 megabytes since memory is cheap? Okay. When you say memory is cheap, okay. Nowadays, okay, now we know we have 8 gig of RAMs and so on, right? But my first computer had kilobytes of RAM, not 4 megabytes. Okay, so and again, this is something that we haven't changed since. But even if you say memory is cheap, it's not. I mean, imagine the following: 4 megabytes. How many threads do you have running? Okay, let's try. I'm just going to look at how many threads I have running here. So let's see, where is my utilities activity monitor? And let's see if it's that cheap. So how many threads, does it say the number of threads that I have? Threads, I have 2,000 threads, okay, right now. And I just have a few things running, right? I mean, I have like what? Zoom probably has a lot of threads and so on. Zoom, the browser, and of course this activity monitor. Now, 2,000 multiply by 4 megabytes. Well, it's suddenly 8 gigabytes. Well, 8 gigabytes just to manage the memory. Okay. even on the memory that we have right now, I have 16 gigs. Imagine half of it is just to manage the memory. It's kind of a waste, right? So no, still, it doesn't work. I hope you're convinced. Okay. All right. So again, this translation here, you see there are kind of two lookups, right? And the CPU has to do this kind of lookup, right? And, you know, if you remember your B58, still, you know, even if it can be kind of hardware and so on, there is kind of like two lookups. You know, one lookup here, once you have this address, you know, you have to do a second lookup. And then once you have this address, you have to do a third lookup, okay? That's at least, you know, even if you do it in one cycle, it's 3 cycles. It's too expensive. Okay, CPU works a lot faster than that. So how can we speed up the process? Well, this is why we have a faster address translation. So here, problem, it's expensive memory access. On every memory access, you know, we have this lookup. So even if we have one page table, you know, I mean, one kind of index, it's still one table lookup, one fetch. 2 page table, 2 table lookup, one fetch. By the way, on the 64-bit machine that we're using right now, okay, on our computer, we have actually 4 table lookups. And 4 table lookups, it's 4 table plus 1 fetch, okay? Somebody is asking, is it related to FAT and so on? We're going to talk about, I mean, FAT is the file system. It has nothing to do with the memory, right? It's a different kind of device. So it's not related, but of course, the same kind of ideas can be brought into a file system. We're going to talk about file system in 3 weeks, okay? So what's the solution for that? To avoid this kind of translation every time, we're going to have something, we're going to have a hardware that is going to speed up this translation. And this is actually inside your motherboard, you have this kind of thing. It's called a translation look-aside buffer. We have a TLB. And you will see it's a special device, a special hardware to reduce the lookup cost, okay? How does it work? Well, a translation look-aside buffer, so again, I told you it's a special hardware, it's going to do the translation for us, right? So what is it? It's actually a small memory, it's a small cache, okay? It's a fully associative cache, okay? All entry lookups can be done in parallel, okay? Well, it's kind of detailed. Usually the cache can have from 32 to 128 page table values, okay? So it's roughly, you know, half a meg small, very fast memory, okay? What's the idea here? The TLB exploits locality. Let me explain that. And let me take an example of, you know, imagine you create a C program where you allocate a buffer, okay? And of course, what are you going to do with this buffer? Well, you know, you're going to read values in this buffer or write values in this buffer, okay? So a buffer, what is a buffer? It's basically contiguous kind of memory addresses well, in memory, right? So contiguous memory slot. So when you write a loop that says, you know, for I equals 0 to, you know, the length of the buffer, and then you iterate, right? What's happening behind the scene? Well, it's, you know, it starts at the address of the beginning of the buffer, and then it increases the address by what's the size of each slot. And you know, for example, if you have integers, it's going to be like 4 bytes, and then, you know, it address it like this, and it keep reading on these slots. So you see here, usually, and same thing, you know, when, for example, the CPU read a program in memory, it reads instruction after every instruction, right? So most likely the next instruction is going to, unless you have a branch, it's going to be the next one. Okay, so it's going to just add, you know, plus 4 bytes, right? It's going to read the next instruction. So most of the time, when you read an address, the chances are, and actually here I'm going to say 99% of the time, the next address is next to it. And meaning the next address, again, if you go back to this, right, to this translation, it means like the physical address, it's going to be kind of the same address, meaning here, only the offset is going to change for a few bytes, but the first 10 bits, I mean, the first 20 bits here are going to be the same, meaning the index are going to be the same. Meaning, why doing the translation again if you just have done it for the previous address? Okay, so that's why here I say, you know, we exploit locality. Okay, so instead, what are we going to do? We're going to do translation once. we're going to buffer it. Okay, and what are we going to buffer? We just need the result. What's the result here? We just need to save what's given 20 bits. Okay, here for the both the index of the page directory and the page table. Given that index, what is the frame? What's the frame index? And if we can buffer that, we don't need to do the lookup in the page directory and page table and so on. We can just do the translation right away. And that's exactly the idea of a page lookup. So here again, you have kind of the page again. This is like it's still in two, right? But it's kind of like you have a page directory and the page table, but it doesn't matter, right? This is kind of like represent some kind of a big page index, and you have an offset, right? So here, if it's in the TLB already, if the page number is inside your cache in your translation look-aside buffer, then you can right away translate it. And because this is hardware, this is going to be very fast. You can do that actually in one cycle. Okay. If it's not, of course, you have to go to the, you go to the what I just explained. You do a first lookup, a second lookup, and so on. But then, important, at the end, once you have done translation, you cache it. Okay. So that's why here it's kind of like the TLB most of the time. I mean, they probably got this result by kind of empirical experimentation, but 99% of the time you hit actually the TLB and not the page table. Okay, not the page directory, basically. Okay, so that's going to speed up a lot, right? So again, this is kind of like explaining re-explaining what I just said. A process is executing on the CPU. Issues like, for example, read an address. Okay, whatever it's at that address, could be an instruction, could be a buffer, could be anything, or the stack, for example. Okay, the read goes into TLB in the MMU, right? This is again part of the MMU. The MMU is the memory management unit. Okay. The TLB does a lookup, and if it's there, common case, it's there, and the page number match the one that is actually in the TLB, and so you can just do the mapping right away, right? There's still like something to validate the address because there are protections and stuff like that and so on. Okay, fine. PTO specifies which physical frame hold the page, and then the MMU combine the physical frame with the offset and so on, and it's automatic. It's all done by hardware, and it's very fast. Okay. There's a question here. How does the PC knows if it's a hit or a miss, though? Well, it's not going to be it's not going to be the PC. What do you mean by PC? Is it the computer, the CPU, or the program counter? Okay, I'm going to guess here you're talking about the CPU. Yeah, okay, CPU. The CPU doesn't care, right? The CPU, again, what the CPU does is just like, it reads the instruction, take the virtual address, give it to the MMU, and the MMU is gonna figure it out, right? Either the MMU, actually, who is doing this translation? It's going to be the MMU, the memory management unit. Again, it's a specialized piece of hardware attached with the CPU. Okay. So the MMU is going to do that. Either it's going to do a TLB or whatever. At the end of the day, the MMU is going to give this the physical address, and the CPU would execute based on that physical address, right? So the MMU does that. So of course, if there is a miss, if the TLB doesn't have the PT mapping for that virtual address, of course now it goes into it does the translation. Okay. All right. So that's kind of like an optimization. Do you have to? I mean, it's good that you know it. Okay, this is of course an operating system, so it's good that you know this kind of thing. Now it's not going to be relevant for Pintos. I mean, it's happening behind the scene, right? You don't see it, but it's happening. It's happening on every computer, every x86 computer. But you don't have to manage that. Well, what you have to manage, of course, is the page table and so on, right? And you're going to do that in Project 3. So now let's talk about swapping, okay? Because that's going to be interesting, and that's actually the heart of Project 3. So what is swapping exactly? So in a way, thanks to this virtual address, you can, so first of all, each thread can can behave as it has access to the entire memory, right? Even better, right? I mean, here I say, for example, that, maximum on a 32-bit system, you can have 2 to the power 32 bit of memory, but in practice, you have a lot less than that, right? So you have less memory than that. So, but even that, the virtual memory system allows you to kind of like allocate more memory than you have physical memory. Okay, so so that's it. So here, what you can do basically is like, every time you need to allocate memory, you just need to allocate a frame. Okay, the idea is the following: what's happening when you're running out of frame? Okay, so, and again, the frame, you don't have 2 to the power 32 frames, right? Depending really on the hardware capacity, right? Some physical address are not accessible because you don't have a physical device that can store that data, right? So what's happening then? What do you do? Well, this is why we're going to talk about swapping, okay? So here, let's see what I have on this slide. Okay, so paging process over time, initially page are allocated from memory, right? At some point, memory fills up. Problem, okay? And allocating a page requires some other page to be evicted. So what do we mean by evicted? Well, okay, so here's the thing. So first of all, you don't execute all threads at the same time, right? So you execute only one thread at a time. Some threads, for example, are low priority. Okay, you have done that in well, you're doing it right now. Okay, no, you did it on project 1. So some threads have low priority, so chances are that they are not going to run, or they're not going to run often. Also, sometimes programs, they allocate something and then they work on something else and so on. So they don't need that memory. I mean, there are plenty of reasons that actually, not every thread is running all the time, and we don't need to access the entire memory all the time. So what we can do is the following: how about if you have a program that if you have a program that wants to allocate memory, and we are running out of memory, how about doing the following? Temporarily, I'm going to take one frame, okay, that has not been recently used, okay, and we will see that it's coming in the next lecture. Okay, but I'm going to take a frame that nobody else is using right now, okay? And I'm going to put it on the disk. I'm going to copy it on the disk. The disk is really the physical hard drive, right? And I put it there. And that means that if I keep a copy, now I can actually use that frame. And I can use that frame for the new memory that I want to allocate. And then I keep going like this. We call that evicting a page, okay? We evict a page to the disk. We call that swapping, okay? Usually we call that swap out, okay? Out of the memory. So we can put it on the disk and so on. And then what's going to happen? At some point, maybe that thread that was having, holding this frame in a way, well, it's going to resume and it's going to work. And it's going to need that frame. Too bad it has been evicted. What's going to happen? Well, actually, you will see we have a way to mark the page directory. Okay, so again, the page directory is about managing the virtual memory, right? So we're going to tag that page as missing, meaning there is no corresponding frame behind that page entry. Okay, so we have a page in memory, the thread is running. It says like, yes, I remember I have allocated that page. It should be somewhere, but we're going to mark it as invalid, saying, hey, I know you have allocated, but right now it's not in memory, okay, because it's on the disk. So what's going to happen? We're going to detect that, and then we're going to actually, the kernel is going to kick in. It's going to take the page from the disk and then copy it back. We call it like swap in, and then we're going to copy it back to the memory, right? So that's basically swapping in a nutshell. Okay, and of course we're going to resume the program and so on. I mean, we update the page directory. Now it says valid, and now we resume. Okay, so again, this is done by the OS. It's completely transparent with the application. I mean, I can tell you, your OS right now does that all the time. Okay, maybe let's see if I have if it shows somewhere. let's see, in my activity monitor, does it say that? I have a lot of memory, so maybe I don't need swap at all, but let's see. Memory, let's see. Physical memory, 16 gig, swap use, you see, I'm using 135 megabytes. So I still have a little bit of swap, okay? We're going to talk about the cache and so on and so forth. I mean, these are other stuff. But basically here, I'm using actually 130 megabytes of swap, okay? So there's a bit of stuff swapped, okay? Question here. Where is the information about the page have allocated swap disk stored? Okay, good question. So, of course, as you can imagine now, okay, very good. You see where we're going. Because we need to manage that swap, we need to kind of keep extra information about, like, yeah, where is that page on the disk and so on and so forth. Yeah, you're just pointing the finger on exactly what you have to do for project 3, and you have to manage that, okay? And we're going to have basically three data structures. One is called the swap table. One is going to be called the supplemental page table, and the other one is going to be called the frame table, okay? And these three actually together, they work to manage the swapping, okay? So that's coming, project 3. I have to say, project 3 is like, it's hard, but students after that, they find it very interesting and kind of like a neat when it works, right? So project 3 is all about making this swapping working. There is an extreme design. Actually, it's not that extreme. It's actually it's some kind of you're going to implement that in project 3. It's called demand paging. What's that? How about the following? Actually, when you allocate a page, when the program allocates a page, we're not gonna allocate it. We're gonna actually mark the virtual memory as, okay, yes, you're allocating a page, but it's invalid, meaning we have not allocated a corresponding frame in the physical memory. And then why is it extreme? Because you're allocating it, but if you don't need it, I'm not going to reserve a frame. And then at some point you are going to need it, and so you're going to read the memory, and because the page is invalid, now actually you're going to allocate. Okay, we call that. It's not. It says extreme. It's just pushing the logic to another step. But this is actually how your OS works. It's called demand paging. Okay, so when you allocate, when you allocate, doesn't mean you're using it. So we allocate directly as a swap, and then as soon as you hit, as soon as you need it, we actually allocate it. Okay, it's called demand paging. You will see you have to implement that actually in project 3. Let's move on. Page fault. So now this is where this is where actually the read, write, execute protection bits are going to be useful. Okay, so here's the thing. For that, so remember, right? On every page table entry, we have bits. Okay, we have the access bit, we have the modified bit, we have the read, write, execute bits, okay, that we're going to use, and we have also a valid bit. It's called a valid bit. I forgot the name. It's called. I should have it somewhere here. Okay, I'm going to check it. It's called. I think it's called the valid bit, something like this. Okay, and here it means basically, is there a physical frame allocated behind that page, right? And as you can see, and it could be that, so in the page directory, for example, if you have not allocated anything, or if you have allocated only one page table, the rest are going to be invalid, okay? And, but when you're also going to evict a frame, it's also going to be written invalid. So the question here is like, how do you make a distinction between something that is invalid because it's not allocated, as opposed to something that is invalid, an address that is invalid because it has been swapped? Well, this is why we need some kind of extra data structures, and spoiler alert, this is actually the supplemental page table. But here, in these two cases, here's what's going to happen. If it's invalid, right away, there's going to be a page fault. Okay, and right now in Pintos, if you have a page fault, it's the end. Okay, the Pintos stops. But at some point, we're going to modify the page fault and say, okay, oh, we have a page fault. But wait, why do we have a page fault? Let's see. So, the CPU, the CPU was asking for that virtual address, and that virtual address was marked invalid in our page directory, okay, or page table, actually. Depends where it is, but in the page table. It was marked as invalid. Why? And so that's why we're going to look at another structure and say, oh, it's because it was swapped. Okay, so everything is fine. Let me bring it back from the swap and then resume. There is no error. Or yes, you are not allowed to access this virtual address because it has not been allocated, or it's actually even outside of your virtual memory. And so no, we're going to stop here. And that's a real kind of a page fault, right? So that's why you have basically two reasons. Virtual page not allocated, you trap the OS, the software takes over, maybe stop the program. This is your classical segmentation fault, or on Linux, for example, or page fault in Pintos. Or no, it was allocated but swapped on the disk, and at that time, no, we bring it back and we resume. It's not an error. Okay. So I'm again going to kind of re-explain what I just say here. At some point, the CPU look at the page table, and here it's written as invalid. Okay, the invalid bit. Oh, well, it's called the invalid bit, not the valid bit, the invalid bit. The invalid bit is set, meaning no, it's not a good address. Okay, what's happening? Trap. Again, it's an interrupt. It's a system interrupt. Okay, the system interrupt is gonna execute page fault. Page fault is the name of the interrupt. So it's going to execute a page fault handler. If it's because it was swapped, okay, fine. I'm gonna the page was actually on the disk. I bring it back into memory, okay? And maybe here I need to actually evict another frame, right? This is another story, but I bring it back into memory. Now I can reset the page table. Now I'm gonna mark it as valid, okay? And then I just restart the function, okay? So here basically, a normal, right now in Pintos, when you have a page fault, it stops the thread, it stops everything actually. But now, now we're actually going to say, no, it's fine, and so on. We're going to resume the program and done. Okay. So there's more on the topic of swapping. Okay, there are plenty of things I haven't told you. First of all, I can, something I haven't told you is like, when the memory is full, what page do you evict? How do you choose? Do you choose randomly and so on? Well, this is kind of going to be another chapter, okay? And that's what I'm going to cover next. So there's going to be more swapping on the next lecture, okay? The mechanism, the policy to evict a page and so on, how to manage it and stuff like that, okay? We're also going to talk about the difference between kernel and user space, because you cannot swap kernel pages, okay, for reasons you see. Okay, so putting it all together, this is kind of, again, repeating kind of the same thing over and over. But basically here you have virtual address. And when you have a virtual address, I'm not going to say you, but it's going to be the hardware that is going to do that automatically, right? The CPU is going to ask the memory management unit, hey, can you translate me those addresses? And the memory management unit, first thing it's going to do, look at the TLB, okay? If it's a hit, meaning, it's inside the cache, okay, I can just translate it right away. At first, still, I'm going to look at whether it's denied or permitted, right? I'm going to check the protection bits. I'm going to check a bunch of things and so on, right? But then if it's protected somehow, when I say protected, is the following. For example, you can mark pages as read only, and it turns out that the CPU asks you for an address to translate because he wants to do a write. So of course, he's going to say, yeah, it's fine. It's in the TLB, but wait a second, you cannot write it. Okay, that's why there's going to be a protection fault. Okay, if it's permitted, okay, no, the address is translated and you're fine. If it's not, it's a miss. Okay, and if it's a miss, then we're going to do the page table walk. Okay, and the walk is basically like, well, is it if it's not in memory? Okay, now we have a page fault. Okay, so if it's marked invalid and so on, we do a page fault, and then this is where we're going to say, okay, is it swapped or not? Okay. Otherwise, we can update the TLB, and we update the TLB here, right? Okay. Now let's talk about some advanced functionality, because of this virtual memory, there are things that now we can do more easily than before. Okay. And the first one I'm going to say, we're going to talk about shared memory. How do we share memory between threads? Okay. And that's basically, on Unix system is basically IPC, communication through pipes, sockets, and stuff like that. Copy on write. So you will see that here, when we swap, you will see, but basically when we swap back to the disk, sometimes we don't even need to copy it on the disk. Okay, you will see why. And then we talk about memory map files and so on. So let's start first about sharing. So the idea here is like, of course, so each thread has its own virtual memory, right? And so they don't interfere with each other, right? Because they never access a memory that has been allocated by another thread, right? Because it's not going to be mapped in the page table. So if it's not mapped, it's because it's invalid, there's going to be a page fault, right? So there is no way that the system, that somehow a thread can read the memory allocated to another process. Okay, that's the default one. But if you want to do that, you could. Okay, so imagine you have two threads and you want to share kind of memory. Okay, you can do that. Okay, on Unix, for example, it's called something called SHMGet, which is shared memory segment, right? The idea here is like you can reserve some kind of memory that is going to be common to two process. Process on Unix, but threads on Pintos, for example. Okay, so then it's easy. How do you do that? Well, you just need to actually have the so one page in the thread A maps to a frame, and then to have another page in thread B. It can be actually a different page, right? It doesn't have to be the same index, but then it points to the same frame in the physical memory. And if you do that, of course, when the thread are executed, they're going to modify the same piece of memory, right? So, so that it works, right? So here, how do you share page? So as I told you, right, for example, here, they can have a PTE, a point table entry, that points to the same physical memory, right? That's exactly what I just explained. All right. Can the map shared memory can be at the same or different virtual address in each process address space? Okay. There are two approaches. Okay. So I told you, right, it doesn't have to be the same mapping. Okay. It is recommended. Why? Imagine the following. Imagine the two programs actually, what they pass to each other's are pointers. Well, they pass pointers, and if those two threads do not have, here, for example, imagine here, so here it look like, it's the same one. Okay, so in the virtual address space, it's going to be the same page index. But imagine it's a different page index. What's happening? It's fine as long as they read data. But if at some point this process say here, okay, I'm going to push a pointer because I want you to look at this piece of information. And he pushed the pointer here. But then this one reads the pointer and say, oh, wait a second. This pointer points to part of memory that has not been allocated. So that's why actually it's better to have kind of the same mapping. Okay? So again, it's share pointer are valid. It's less flexible because you need to find this, a page that is free on both process, right? But it works better because the pointers are valid. You can have different mapping, but the problem is like pointers are going to be invalid, or you need to kind of translate them. Okay, maybe they can send offset to each other. Yeah, exactly. So that's Anton is right. That can be a solution as well, right? If you're working in project 2, this is exactly what's happening in a nutshell, right? When you have, it's kind of the same idea, right? When you have a user thread that push a pointer to the stack because it's going to do a system call. And then this pointer is valid inside the mapping of the user thread. And then you execute the syscall, and now the kernel execute, and the kernel is going to read that pointer from the stack. But that pointer is valid in the user space. So you need to translate it into the kernel space. That's why we need to translate a user virtual address to a kernel user address. Okay, it's okay. We do that because the system calls are quite I mean, they're very standard and so on. We can do that easily, right? And you are doing that in project 2. So here we can do the same thing, right? If it's a different mapping, okay, it's the same thing between 2 threads. Yes, as Anton say, it's just a matter of like either providing an offset or providing some kind of a way to translate from that kind of virtual address A into virtual address B and so on. Okay. Question: when you reinstate a swap page, could you have a different physical address before it was put to swap? Yeah. No problem. This is exactly what's beautiful about paging. It's completely agnostic to what it is, right? You can actually when you swap back again, you can put it in a different place, right? What matters is that every time you're going to swap it back, you're going to update the page table. You can say, oh, now this page here that was swapped, now it's in frame, now this time I put it in frame 20. But then you swap it out again for some reason, you swap it back and say, oh, now it's in frame 32, but you just update the page table. So every time you bring back the page, the frame, you update the page table. So it's not a problem. Yeah, Anton answers here. I think it's handled by the kernel by updating the page table. Yeah. Now, again, as long as you keep this page table kind of organized and always have the right mapping and so on, it's going to be fine. So that's why you can even relocate stuff in memory and so on. No problem. Swapping works well. Copy and write. What's that? So an OS spends a lot of time copying data, right? For example, the system calls, you are doing it right now, we have to copy arguments and so on and so forth. Sometimes you copy the entire space when you do a fork. Remember when you do a fork? When you fork a process, you copy the entire virtual address to another one because you create a new process, right? Basically, only on Unix. But it's kind of the same as copying a new thread in Pintos. No, in Pintos they don't do clone, but yeah, okay. But kind of the same idea. You create a new space. So copy and write. The idea is the following. So the question here, do we need to copy right away? Can we avoid copying? Because copying is expensive, okay? Can we avoid copying? Well, why not? Why not? So, and here I'm going to use the same kind of idea that I used previously. Let me show you an example, okay? So imagine the following. Here you have a parent process. And the parent process, so that's its virtual memory, but its virtual memory really what's allocated, it's this. This is a frame, that's one frame allocated, that's one frame allocated, and then there's a third frame allocated. I mean, 4. 1, 2, 3, 4. So what's happening when there's going to be a fork? When there's going to be a fork, you're going to create a child, and the child needs to have its own kind of address. So without doing anything, okay, so what you need to do is we need to actually allocate, same thing. The data that were here, we need to duplicate them. What does it mean to duplicate? Well, we need to duplicate the frame and then have the kind of the same virtual address pointing to now this time another frame. So you have to copy that, right? But what if we do the following? Instead of copying, because copying is expensive. Again, let me backtrack a little bit. The problem, when you fork a child, they will have the same variables. But at some point, if the child modifies the variable, then the variable is going to be kind of different from the one from the parent. But if the child doesn't modify it, it's going to be the same, right? So how about keeping it like this? And so what we're going to do is the following. When we fork a child, we're going to assume that all the variables are going to be the same. And for that, we're going to let them share it. How? We're going to just have the child pointing to the same frame. Okay, so we have its own, of course, page table and so on, but we're gonna point it to the same frame, meaning we're not gonna actually allocate memory for the child. Okay, we just no, of course, I mean we only allocate the new page table and so on, but they're gonna point to the same frame. But what we're gonna do is the following: we're gonna mark those frames as read only. Actually, here they say it's gonna be on no, yeah, it has to be in both. It has to be on both. We mark it so on the parents and on the child, we're going to mark those frames as read only. And again, remember, right? We can do that at the page table entry because now we have protection bits. And now we're going to force a read only. Why? So if it's read only, what's going to happen if you try to write? If you try to write, there's going to be a page fault. Okay, because you try to write a page that has been tagged as read only. But then you're going to handle it. You handle the exception, and then you're going to say, "Oh, why is there a problem? Oh, because it's read-only." But why was it read-only? It was read-only because I did this trick of sharing the thing because it's a frame that is currently shared by the parent and the child. Okay, fine. So you know what I'm going to do now? Because of this page fault, now I'm going to duplicate it. I'm going to duplicate. I'm going to change the page table of the child. I'm going to mark them as right now. And again, I'm going to resume the process. You see? So here, in a way, when I fork a child, I'm going to let them have shared the data, right? Although this is not what I want, right? I mean, from the user perspective, I expect them to have their separate life. But I'm going to let them have shared at the beginning. And then only if you do right this time, it's like, okay, fine. You cannot share it anymore because now there's discrepancy. I need to duplicate. I update your page table and then done. It's quite smart. I mean, if you understand it, it's quite smart, right? It saves time, it saves space even, and so on and so forth, right? Because still the others, if you don't write on the other on the other data and so on, you can still share. Why not just copy instead of changing all the entry in the page table? That's what we're doing. We're copying, but if you copy, right? If you copy, we need to change, right? Because now if they write that, I mean, this is the memory of the father of the parent, right? So you don't want to modify that. So you need to copy, and then now you can write on that. I'm not sure I understand your question, Mohammed. I hope. Okay, I hope I answered your question. Okay, but the idea here, we're going to copy only when we need it, and that's going to save. Well, it's going to be more efficient. Okay, map files. Something also that this is something also that you have to do for assignment project 3. So let me explain what's map file. So let's go back to your favorite programming language, and here it can be whatever: Python, Java, C, you name it, right? It's kind of convenient, right? When you open a file, you say, okay, open file, and then you get something we call a file descriptor. And then from that file descriptor, it's very easy to navigate into the file. Why? Because we start somewhere at the beginning of the file, and then we just increase some kind of an offset to read actually the stuff from that file. So in a way, we think about a file as if a file was in memory, and we just access memory allocation, memory addresses, right? But it's not like that. I mean, behind the scene, a file is stored on the disk. Okay, and the disk, actually, we're going to see that later when we talk about file system, we don't access it like that, right? We have to pass some kind of disk sector and so on, right? So we need to do input-output. So how does it work? How come, as a programmer, we look at files as if it was in memory, although in reality, it's actually on the disk, and the disk is under the I/O. It's not like the memory, and we need to access it differently. Well, that's because actually what the OS does, when you open a file, what it does, it reads that file and then copy it into a frame, okay, entirely, not the entire file, actually. It copies just the first part, and then if you need, it copies more. It copy it and then give you the address, and now you can actually interact with the file as if it was just like, in memory. And that's very convenient for us programmers. Okay, because now we can iterate, we can do, we can write a loop and we just address it and so on. It's the same as basically accessing a buffer. Okay, when we open a file, it's like we have a buffer. So that's how it works, right? So we, map files, it's like each process, we bring it back into memory, and now we can use it as like memory, right? So initially, we can do the kind of same thing, right? All page mapped to a file, they are invalid, meaning, we actually don't read the file. And it's like domain paging again, right? But now applied to file. When the OS reads from a file, then an invalid page is accessed. Invalid, if the page is invalid, it triggers a page fault. The page will look at it and say, oh, okay, that's because it's a map file. The map file has not been read. I read the file from the disk, bring it back to the memory, and that's it, right? So you see, it's kind of the same idea. It's just a twist to make it actually more efficient. Okay. And so on and so forth. And something interesting, maybe here I talk about, no, I don't talk about it. I talk about it here. Something interesting. What if you don't write the file? Okay, so if you don't write the file, okay, so no, it has not been modified. What if you have a map, so you have a frame that contains data about a file. So basically a map file. What if now you want, I'm going to talk about swapping again. What if you want to swap that page? Well, guess what? Do you need to actually copy that frame into the swap directory? It's kind of duplicate, right? Because you already have this file copied on the disk somewhere, right? So if it does not change, when actually you swap a map file, you can just remove it. That's it. You mark it as invalid, and that's it, because when you're going to read it, it's still going to read it from the file, meaning from the file system, not from the swap. If it has been modified, the only thing you need to do is actually save it. How about you save it into the file? Okay, because you are writing in memory. So you just save it into the file. And then you can just evict it. But when you evict, you don't need to write it in the swap. That's why I can tell you, in the swap, you will never find frames that have data about files. Okay, because then otherwise it will be duplicating. Okay, so again, that's a small optimization. You're going to do that in project 3. Okay, advantage and drawbacks of map files. A file is essentially a backing store for that region of virtual address and so on. So it's good because you can just use pointers. For the programmers, it's perfect. We like map files, okay? But now, we need to check, the process has less control over data movement, right? It's going to be the OS who's going to read and write the files and so on. You don't control that. It's going to be the OS who does that. I mean, it's not a big drawback, by the way. We have been, you guys have been using files since at least AO8, and, it's completely transparent. You don't see all this stuff. And it doesn't work for like what we call streamed input-output, like pipe sockets and so on, right? Because, well, they are not really files, okay? But yeah. Next time it's going to be in, 10 minutes, okay? So let's do that. Let's take a break because we need a break. Let's come back at 12:15. Okay, we come back at 12:15. All right, and we are back. So there's a question here. I'm a bit confused regarding the memory map files. I'm wondering what loads a file content loaded into memory. Is it done by an interrupt handler that is called when a page fault occurs for memory map files? So, well, okay, let's start from the user program, because again, that's what what's happening. So, in the user program, you're going to use something like open, for example, in Python or in C. Same thing in C. You're going to open a file. So when you do open, it's called a library, and that library behind the scene, it does a system call. Why? Because we're going to need to read that file, and it's an input-output, and only the OS can do input-outputs. So there is a system call. The system call is actually see that you want to open a file, and here what it's going to do is the following. So if you're doing it as a map file, okay, that's what usually happen. It's like, okay, we are going to actually, the OS is actually going to read that file, okay, allocate some memory, and then copy the file on the frame. Again, if it's non-paging, actually, it's not going to copy it. It's just going to allocate the page directory and say, okay, that page is going to hold the file, mark it as invalid for now, and then resume. And then what? Now the program continues, and the program now reads the file. If you read the file, there's a system code and so on. The system, sorry, no, there is no system call. Now you read the memory. The memory is marked invalid. Okay, there is a page fault. Page fault is handled. You see that it needs the file, reads the file, bring it back, and so on. Resume. Okay. So now actually the file has been copied in memory. It's now in. I mean, you can use it at the user level. Okay. I hope I answered your question here. Okay. All right. So let's talk about memory management. So, I mean, it's kind of a weird title because I've just talked about memory management from the beginning, but there are more questions that we need to answer. First of all, how do we allocate free space? Okay, how do you know which frame is free or not? Okay, so we're going to do that. And is there a best strategy to actually allocate space? Yes, we'll see. How do we evict pages from memory? You know, when we do swap, basically, how do we choose which frame to evict? Okay, and this is going to be the page, something we call the page replacement algorithms. And you will see that there are plenty of algorithms. Okay, actually, I can tell you, Windows and Linux use a different algorithm. That's interesting. And the other one is like how much memory to give to each process. Okay, so and you will see that's going to work in set model. So right now, you know, what if you have one process in your computer that needs so much memory that is going to eat up the memory of other process? Meaning, you know, of course, if it eats a lot of memory, maybe it's going to have swap. It's going to trigger the swapping and so on. It means all the other processes are going to swap as well, right? So how about maybe we can constrain, Windows does that, by the way. We're going to constrain what the program can consume, and beyond this a certain limit is going to use the swap automatically. Although the others, they can still actually allocate directly from memory and so on, right? We'll see that it's going to working set model. And here, how do you decide actually? How do you know how much memory a process needs, right? By the way, Linux doesn't do that. Okay, it's more like a Windows actually, I think. Okay, so let's start. So first of all, let's manage free memory. How do we manage free memory? So again, we have to distinguish between two things, okay? One, there is static allocation, which is basically usually we call stack allocation, okay? And usually this is fixed in size, meaning when you actually compile, when you write a program in C, okay? So most of the variables that you declare, they are actually allocated on the stack, right? Except when you do malloc. Malloc is dynamically allocated. So in C, for example, you allocate that, you tell exactly how much you need, right? When you create a buffer, when you create a variable and so on, you have types and stuff like that. So when we compile, we know exactly how much space we need, okay? And actually we can infer that. So, you know, at compile time, we know exactly how much we need. So here it's going to be easy, right? Because if you have a program that only uses static allocation, we know exactly how much memory to allocate. Okay, but how about dynamic allocation when you have malloc? When you have malloc, it depends, right? Because you're going to do malloc of a number that this number might be, you know, it depends on the execution and so on. So it depends. And this is going to be done at runtime. So for this one, it's going to be kind of hard, right? What I'm saying here, why I say it's simple is because again, here with the stack, for example, you know that the stack is not going to grow statically. You know that the stack has some kind of a limit. It's not going to grow beyond certain things. Okay, I mean, even considering like recursive functions and so on, because you have actually a maximum recursive depth and stuff like that. But with dynamic allocation, you have no idea, right? It can be possibly like, you know, possibly many. So this is why it's going to be hard. It's going to be hard. Also, something kind of useful is like when you allocate the stack always grow and shrink, kind of like, you know, but it's always contiguous. The stack is always contiguous by default. Malloc, you can start contiguous, but then if you do malloc free, malloc free, malloc free, well, you might have, pieces that are allocated, pieces that are free, pieces and so on. And that should remind you fragmentation. Okay, we're going to have fragmentation inside with the dynamic allocation. Okay, so let's look at all of that. So again, so heap allocation, it's about managing continuous range of logical addresses. Okay, so basically, we allocate one page or maybe multiple page. That's going to be the thing for our heap. And then when we call malloc, okay, malloc is again a user kind of thing. We need to allocate stuff. Okay, and here it's going to return a pointer to a block of memory of at least size bytes. Here, sometimes it's more actually, or null if you are running out of memory, and then free that memory, right? That's basic stuff you have done in C. So when you do heap allocation, so here, well, so if you don't do any free, okay, it's easy, right? You just allocate, and then if you need more, you have another malloc, you keep allocating, right? And at some point, okay, you're gonna have maybe you might run out of heap, but that's okay. So you can just allocate it like that. Problem here, if you do free, you're going to create small holes here, okay? And again, we call that fragmentation, okay? So it's a lot of free space that cannot satisfy any request. So, so here, what is fragmentation really, okay? Again, it's the inability to use free memory, okay? And why do we have free memory? Because variables or objects or whatever, things that you allocate, they have different lifetime. And because they have different lifetime, sometimes they will die, and then they will free the space that they occupy. But also because they have different size, it's hard actually to deal with that. So here, if all requests have the same size, then there is no fragmentation, right? Because you can reallocate that space. But because they are different size, you have fragmentation. So at some point, there's going to be some important decision, right? So, and again, I just want to back up here a little bit. I'm going to talk about allocating free memory. This is going to be true for when you do malloc and so on and so forth, but also when you manage a swap, when you manage all kinds of things. Okay, the swap at least it has a good property that they're all of the same size, right? But here, so placement choice. So where in the free memory do you put a requested block? Okay, so ideally, okay, you want to put it in a place that doesn't cause fragmentation, okay, or in the future. But in general, that's impossible. Okay, you don't know what the future is going to be, so that's going to be hard. So you're going to try to do your best to put it some places. Sometimes you have to free some blocks to satisfy smaller requests. For example, here, well, not here, but imagine you have a big block of 30 and you need only 10. Well, you have to fragment it and say, okay, now I have a block of 10 and then a block of 20, and you're going to allocate the block of 10. But at the same time, when you free, now you can actually merge them back. So for example, here, imagine, you have a block of 20 that is free, 20 that is free and 10 that is allocated and 30 that is allocated, and you free the block of 10. Now you can actually merge them. We call that actually code sync, these two blocks, and say, now you have a block of 30, right? So there is a theoretical result, and that has been proven that it's impossible to avoid fragmentation to start with, right? Because for any algorithm that you use to manage your free space, you can always find a sequence of allocation and deallocation, malloc and free, that is going to defeat your algorithm and create a lot of fragmentation that you cannot use, right? So that's it. So it's supposed, don't try to find the perfect solution. It doesn't exist. So we're going to try to find again, the best one, but not the ideal one. So when we talk about a memory allocator, what does it do? Well, it needs to track which part of memory is in use and which part are free. Okay. Ideally, no wasted space or no time overhead. Okay. So no, when you do a malloc, again, think about that way, right? A malloc is going to be a system call. The system call is going to say, okay, now I'm going to allocate space on the heap, but I need to kind of like, manage my free space, okay? Because you're not going to keep allocating pages and pages, right? You need to kind of reuse stuff that have been okay, there's a question here. Why do we care about fragmentation if the virtual physical address mapping fragments the data always? Okay, okay, I see the confusion here. Okay, let's go back. When we talk about memory and how to manage in memory, when we talk about virtual memory, we talked about segments at first, segmentation, and then we talk about paging, right? And I told you the good thing with segment is like, you allocate exactly what you need, but then you create external fragmentation, okay? But no internal fragmentation because you allocate exactly what you need. And we say, okay, paging actually, with paging, we don't have external fragmentation because you just allocate 4 kilobytes block. So that's good. But then we have internal fragmentation. Okay. Here, again, one step beyond that, which is, imagine the following. Imagine you write a program in C that uses malloc, okay? And malloc, usually when you do malloc, what do you need? You need maybe an array of what? I don't know, 16 bytes, 20 bytes, 100 bytes, depends what you store and so on and so forth, right? So for each variable, you're not going to allocate one page, right? It's going to be a waste of space, right? So probably what you're going to do is the following. You're going to allocate one page, okay? You're going to allocate one page, and then within that page, you're going to try to put as much data as possible, right? Depending on the malloc free, malloc free, malloc free. But you're going to say, okay, that page is going to be for the heap, right? You have, again, another page or several pages for the stack, okay? And again, you're going to have one or several pages for the heap, okay? So what you could do, and again, I'm going to go back. Okay, maybe I went a little bit fast. What you could do, I'm going to go back to this, right? This drawing, okay? What you could do here is like, as you have malloc, you just allocate the malloc here within the page. At some point, you're going to reach the limit of the page, so you just allocate another 4 kilobytes page. That's okay. But if you do that and never free, you have a problem, right? Because you have something we call memory leak. Okay, at some point, your program will handle, imagine a loop that do malloc all the time, right? You're going to allocate memory and so on, and you're going to run out, right? So, of course, there's swapping and so on, but we want to be more mindful here. So that's why at some point you can also free, right? So if you free a piece of memory that you did malloc before, well, you can reuse that piece of memory, right? Or even better, if you do a lot of free, you can even free the page. Why not? If the page is empty, at some point you can free it, okay? So by doing that, you are gonna be more mindful of the memory and avoid memory leak, right? That's the idea. When you write a program in C, you do free because you know that you're gonna free some memory, right? But behind the scene, what does it mean freeing memory? If you allocate 12 bytes, are you really freeing 12 bytes? Yes, you're freeing 12 bytes, but you're not freeing the page, or maybe you're freeing the page for the programs also, right? If you deallocate a lot of memory. But imagine, here, this can be, for example, one page, and because you have done a bunch of malloc and free, you have small holes here that you can maybe put some data. Okay, so it's about allocating dynamic memory, right? The heap, basically. Okay, so that's what I'm trying to do here. Okay, so you see, it's kind of like, I'm not going to say it's orthogonal to the page and segmentations and so on. It's more like, within a program, when you allocate, basically, when you do malloc. Okay, but of course, it's based on that. Yeah, so a question about Pintos. So yeah, so in Pintos, Pintos, you work at the low level, right? So on Pintos, on the kernel, you can do pallocate page. That's going to allocate one page, and one page is 4 kilobytes. Okay, so of course, and I hope for project 2, even project 2 or project 3, project 2, every time you allocate one variable, I hope you're not allocating a page, right? Because you're basically, we are going to run out of memory very soon, right? A page is 4 kilobytes. You should use these 4 kilobytes. Okay, so It's interesting, but a user program will not do plog get page, never. Okay, so it will never do this plog get page, right? It would probably use malloc, and that's why here I'm answering the next question. Here, that's why we have malloc. Malloc is to kind of allocate a page within a page, yes, or within some kind of a free memory that you have, right? Yes, and malloc and free behind the scene, what you expect is gonna do that to avoid fragmentation. Okay, so if you free a memory, now you can reallocate it to something else, right? That's what we are trying to do here. Okay, I hope I wasn't confusing. Okay. Okay, so let's go back. So here, imagine we have one page. One page is 4 kilobytes, but the user needs to do malloc and free, and so on. So how do we manage this free space in a way, right? And at some point, if we do too much malloc, we're going to again allocate another page, and now the heap is going to be 8 kilobyte in memory, but really there's going to be like maybe a few things allocated. Okay. So fragmentation is impossible to solve. I've covered that already. I've covered all of that. Okay. So what is a good memory allocator? Of course, a good memory allocator is going to track the memory that he is using, which part are free, which part are basically not free. Okay. And you want to do that very quickly. Okay, as quickly as possible. What the memory allocator cannot do, it cannot control the order and the number and the size of the requested block, because it comes from the program, so you don't know that. And you cannot know what's the future allocation. You cannot predict what's going to be, right? Because it's going to depend how the program is going to execute. Right? So what makes a good memory allocator? The one that will minimize fragmentation, that's what we want to do. And we want to avoid compaction. What's compaction? You might say, no, once I've reached that, how about, I reorganize things? Okay, I kind of like, move data so that they kind of like next to each other. It's hard. And it's actually almost impossible, right? Because when the program handles pointers and so on, you need to update pointers and stuff like that. It's a nightmare. So most of the time you cannot do that, and it's not efficient. It takes time. Okay. So let's start first. So how do you track memory allocation? You can do it in many ways. One is to actually have something we call a bitmap, and that's going to be very useful. By the way, you have a bitmap already implemented in Pintos. Okay. So what do? You take a piece of memory, and you're going to use bits for to map your memory. So for example, here, imagine the following. So here, how many bits do I have? 1, 2, 3, 4, 5, 6, 7, 8. Well, let's imagine there are 10. I don't want to count all of them. Imagine you have 10 slots. So with 10 bits, you can basically manage 10 bytes. Okay, if you allocate in blocks of bytes. Okay, you can allocate 10 bytes. Right, and then you can just put one. Usually you allocate 4 blocks of 4, right? 32 bits address. But here, having a 1 means this block is taken, the other one is free, and so on. So imagine you have your bitmap here, and then you can have your memory following, and you can say no, the first block here taken, the second block taken as well, the third block taken, and this one free, and so on and so forth. Why is bitmap actually good? Because, well, first of all, it's compact. Okay, you can actually. I say slow. It's not that slow because you can always use some kind of a bitwise operation to find actually which one are zeros and stuff like that. So it's kind of like you can do it, but still it's actually slower than other ideas. So other ideas are follows. As follows. So you can track, how about tracking it as a list? Okay. Oh, sorry. Isn't the bitmap inefficient because it takes 1/8 of allocated memory? Well, no, it's not 1/8 because I told you, right? It's usually like 4 kilobytes. 4 bytes is going to be 1 slot. But still, you can argue it's going to be like a 1/32 of your memory. Yeah, why not? Yeah, it's inefficient. Yeah, you will see that the ones I'm going to talk about, they still require a little bit of space, actually. Okay, at some point, if you need to manage your free memory, you need to store information about those free memory, right? So you have no choice. The other one is like, you can maintain some kind of a linked list of allocated and free segments, right? So the idea is to track a linked list. So you can have a free list, saying like, from that address to that address, it's free. From that address to that address is and so on. So that's kind of a free list. There's something more efficient, which is an implicit free list, which is you actually here, you say, okay, you're going to store in these 4 bytes, for example, if it's a block, okay, 4 bytes, you're going to store the fact that, okay, the next 4 bytes are allocated, okay, and that's it, right? You say no, next 4 bytes are allocated, then you jump to this one, say the next 5 bytes are free, and so on and so forth. So here, searching for a free block is linear in total number of blocks, meaning here, you start here, okay, it's allocated. Imagine you're looking for 5, okay, or even 3. Depending on your algorithm, you're here, it's allocated, you go here, oh, it's fine, I can allocate here, okay? So searching for free block is linear, and each block has a header of recorded size. Okay, I've said that. There is also something called explicit list, okay, which is, now you have pointers, and rather than saying 5 and, doing arithmetics, you can just follow pointers that points to the next free one. And you can have a double linked list actually to that you can go back and forth, right? Sometimes it's going to be useful to go back and forth. So that's another way. Which one is better? Well, let's see. So here, I mean, actually, regardless whether you have actually a double linked list or just like numbers and just the what they call the implicit list, freeing blocks, you have to do some kind of merging. So, for example, here, imagine you are freeing those 4 blocks that were allocated here. Okay, so because actually you have 1 block to register the length, but then 3 blocks were allocated. There was a malloc 3. So now you free it. If you free it, you can just mark it as free. But then here you see what you have fragmentation because you have 5, 4, and 2. What if now you want to allocate 10, for example, right? Here, you're not going to find 10 unless you actually kind of merge these 3 things and say 11. Okay, here there's going to be a block of 11. So we call that like coursing. So you see here when you free, you kind of have to look at the previous and next one to see if they are free. And if one of them or both are free, you need to actually merge, right? So there is a little bit of operation here. Placement algorithm. So here, when you have that kind of representation, for example, or even double linked list and so on, which algorithm is first? Imagine here the following: you want to allocate, you have malloc 3, right? Again, on this configuration, imagine you have a malloc 3. You can put it here or you can put it here. Which one is best? Okay, well, let's try. We're going to see actually 3 algorithms. Okay. There are many actually. People have proposed a bunch of stuff. There's first fit, best fit. We're going to see those 2, but let me tell you, Linux, for example, use something called the buddy system. So that's why I'm going to show you this one. So what's best fit? Best fit here, the idea is like we're going to minimize fragmentation by allocating space from a block that leaves the smallest fragment. Meaning you go through the entire list, okay, and you're going to find a block that leaves the minimal fragment. So if you're looking for 3, you're going to go and look for a block with exactly 3. I mean, that would be the best, right? But if you don't find it, you're going to find the smallest block that will leave the smallest fragmentation. Okay? So that means at least you need to go to the entire thing, right? So that's why for this kind of thing, the best is actually to have some kind of a data structure, which is a list of free blocks, okay? And each has a header holding the block size and so on, and a pointer to the next block so that you iterate fast, right? And then just keep as you evolve, it's like finding the minimum into an array, right? You iterate to an entire array, you keep track of the index or the address, and then at the end, this is the one, right? So it's basically ON to find the best fit. The code, you search for free list closest to the size of the request and so on. Of course, you can stop. If you find the one that is exactly what you need, you can stop before. As opposed to another one is first fit. What's that? You pick the first block that fits. Okay, very easy. You're looking for a block of 3. the first one is 32. It doesn't matter, use 32. Okay, and of course, use 32. You're going to update to now have a remaining free block of 29, right? Of course, you always do that. So you scan the list, take the first one. So this one is super fast, right? In a way, you allocate very quickly. Let's see how they behave in terms of fragmentation. Okay, and for that, maybe I'm going to have, imagine two things, right? Imagine you have two free blocks of size 20, one of size 20 and another one of size 15. And imagine the first workload. So the first workload here is like alloc 10 and then alloc 20. If you look at best fit, you know, for the alloc 10 is going to look at the minimum one. So here it's going to look at 20, it's going to look at 15, it's going to say, okay, I'm going to put the 10 inside the 15. And then you say alloc 20, oh, perfect. Okay, I'm going to put the 20 inside here. If you do the same workload for first fit, actually now it's phase. Why? You do alloc 10, we do the first one. The first one, we have 10. 10, and we have a remaining of 10. And then we look at alloc 20, too bad. We have only a block of 10 and a block of 15. We fail. So you see here, you might say, oh, wait a second, best fit is better. Well, let's look at the second example here. Imagine now I have the same kind of block, 20 and 15, and I have alloc 8, alloc 12, and alloc 12 again. If I do best fit is going to do the following. First, alloc 8. Alloc 8, we try to find the best. The best is actually the 15 because it leaves the minimum fragmentation, right? So it's 8, and we are left with a block of 7. So now we have a block of 20 and a block of 7. And then we do allocate 12. Okay, fine. You know, here doesn't fit. So here it's going to fit in here. And we are left with a block of 8 and a block of 7. And then alloc 12. Fail, we cannot allocate. Although first fit, you know, first you do allocate on the first block. So now we are left with 12. And then we do 12, 12 again here. And then 12, 12. And it's fine. So you see here, which one is the best? Well, again, let me tell you, there is no best algorithm that beats fragmentation. I told you, right? There is a result that says you can always find a sequence of allocation that is going to defeat your algorithm. And here, this is a two example. Here I defeat first fit. Here I defeat best fit for the same kind of free block configuration, but different allocation sequence. Okay? Wait, why don't we merge block 5 and 15? Oh, wait a second. Because these blocks, maybe in the middle, there is something else, right? Merging would means moving data. And moving data, it's not a good idea. It's hard to do because you have to change pointers and so on in the program. It's hard. Okay, so we don't do that. Comparing first fit and best fit. So which one is best? Well, okay, first fit is simplest and fastest because we're going to fit the one, and maybe the most efficient. Actually, this one, it's kind of like a very good, right, in terms of performance and so on. But it may leave like many small fragments. Okay, the first fit maybe tend to fragment a little bit more. Okay, sorry. Best fit in practice, you know, it's sorry. The leftover fragments tend to be small, okay? Well, small means also they're unusable. But in practice, you know, it's best for actually storage. When you have a storage, this is more mindful of the space, okay? But which one is better, you cannot tell. There is one actually that Unix use, which is quite smart. Let me tell you how it works. It's called the body allocation. And this one is actually efficient to manage and so on. And it doesn't leave like a lot of fragmentation. The idea is the following. We're going to allocate blocks in powers of 2s. Okay, so 2 to the power k. So that means, for example, like, no, if you, so it's either like, no, 8, 16, 32, 64, 128, and so on, right? It means if you need only 10 kilobytes, you're going to allocate 16 kilobytes, okay? And you're going to have fragmentation, but it's okay. You will see why it's actually good. So, the body allocation, in the code, actually, so when you have a big block like this, imagine you need to allocate 8 kilobytes, you're going to do the following. You're going to divide this one into 2, and then you're going to take this one again, you're going to divide it into 2. And then you take this 16 bytes, you're going to divide into 2 until you find 8 kilobytes. And for example, if you need to allocate 6, that's what you have. And this one here is going to be the body of this one. And this one is going to be the body of this one, and this one is going to be the body of this one, and so on. Why is this body actually quite good? So first of all, dividing in powers of 2, this is something we know how to do well just by doing bitwise operations. So that's going to be fast. Also, we're going to keep some kind of a free list of the body, and you will see how efficient it's going to be in the next one. When you free, it's simple. When you free a block, you're going to look at the body, and you know the body because it's powers of 2. It's just 1 bit different. Okay, that's what's nice with powers of 2. And you're going to look at the body. If the body is free, you're going to merge them, and then you do that recursively. If this one is free, you look at the body, you merge. If this one is free, you look at the body, you merge, and so on and so forth. So you can do that very recursively just by doing 1 bitwise operation of checking the body and then merging them. So let's see how this works. So imagine the following. Here we're going to say we have a free list, okay, of 3. So 3 is actually 2 to the power 3. Okay, that's why here it's going to be 9. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 8. Yes. Okay. So yeah, 2 to the power 3. So it's not 9. It's 8. So 8 here, 2 to the power 3. So here we have a free list of a block 3, and here it starts at 0. Okay. And then what? And then we do alloc. And we're going to allocate in powers of 2. Imagine we allocate a block of size 1. Okay. So 2 to the power 0 block of size 1. So we're going to allocate this one here. So here, if we allocate this one, we're going to say the following. Oh, now my free list in the past it was 3, but because I divide, now I have the following. Now I have a free list that starts at of size 0 and it starts at 1. Okay, so meaning I have 1 block free here. And then on 2 to the power 1, so of size 2, I have 1 block that starts at 2. And then I have 1 block of 4, 2 to the power 2, that start at 4 here. Okay, so that's my free list. You see, I maintain kind of 3 lists here. And then I have, again, an alloc. Now this time it's alloc of 4. Okay, it's easy. If it's an alloc of 4, I just go there and okay, now it's allocated. You see, right away, if I don't have to divide, it's kind of right away, I find my block. Okay, so I find my block, I remove it, and now I have, it's like I have an empty list if you want, right? So now I'm left with this. And then I free P1. When I free P1 here, I'm going to free this block. So I'm going to look at it, it's block 0. So where is the body? It's block 1. Oh, but wait a second, block 1 is free. So because it's free, I'm going to say, okay, I'm going to compact them. And now I have a block, sorry, this one, now I have, if you want, I have a free list of 1 that start at 0. But wait a second, this one is body, this big block here is body with the block that starts at 2 as well. So now I can actually compact them. And now what I have is, I have a 2 to the power 2, so a block of 4 that start at 0 here. Okay, and now if I free the other one, same thing. I'm going to free this one. I'm going to look at the body. The body is actually free, so now I can merge them, and now I have a free list of 2 to the power 3 again. Okay, so it's quite convenient. So doing this kind of like powers of 2's operations is quite efficient in terms of bits, right? It's only flipping 1 bit every time. And it's a good way to actually manage it. Linux works like that. Okay, that's why it allocates in powers of 2. This is why, by the way, if you take a Linux program and you do a malloc, it's always going to allocate more memory than you need because of this kind of thing. Okay, but again, it allocates more memory, but it's easier to manage, and it's actually better. It's efficient to actually free and so on, right? And to allocate. So advantage of the buddy system, it's fast for the search, okay? And it's fast for free. You avoid iterating through a free list, okay? Because you have actually different lists of powers of twos. So you just take the first one every time. You avoid external fragmentation because you always request the powers of two, right? So you don't have kind of external fragmentation. And you keep the physical page contiguous, okay, always. Because again, this malloc is going to be inside the page. So you start with a 4 kilobytes page, and then you can divide that page, right? If you need more, you just allocate another one, okay? Used by Linux and FreeBSD. Question, if the user allocates not in powers of two, can the user use the memory up to the next power of two? No. So if I understand the question correctly, so imagine the user doesn't allocate in power of two. For example, it allocates 10 kilobytes, for example, and instead of that, he's going to get 16. Can you use those extra thing? No, because if he needs, again, to do malloc, he's not controlling the memory, right? It doesn't see that. Again, the program is going to do a malloc, and the malloc is going to allocate another free memory, right? It's not going to keep track of this. In a way, it's not going to keep track of internal fragmentation. It's kind of the same idea of like external and internal fragmentation. You know, what we had at the level of pages, the fact that the page are of fixed size and so on, we had no external fragmentation, but a little bit of internal fragmentation. Here, it's kind of the same thing. So we are more flexible because we can actually at least have different block size, but those blocks are always in powers of two, and those power of two actually contribute to avoid external fragmentation, but it generates a little bit of internal fragmentation. But again, it's a good trade-off. Okay, I hope I answered your question here. Okay, page replacement. Let's see. I have only 6 minutes. And I think this is going to be, yeah, it's going to be bigger. So let me do that. Let's see, you need that for project 3, but you're not going to start project 3 next week. So, okay, I'm still good in terms of the schedule here. So let's do that. I'm not going to start this. I've just shown you how to manage memory. By the way, Pintos managed the free memory for you, right? But it's interesting to look at how they do it, okay? So look in the code, see if they use the buddy or they use best fit or first fit. It would be an interesting thing to look at. Okay, so the next thing we're going to do next week, we're going to talk about page replacement algorithm, which is, in a nutshell, how do we select the frame to evict when we do swapping, okay? Again, this is going to be needed for project 3. All right, so that's it for today. Again, good luck on the project, on project 2. If you have questions, I have office hours at 2 p.m. And on that, well, have a good weekend. Bye.